Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review all of the trigonometry you need to know for the final exam. So I'll cover all of these topics on your screen. Let's get started with right-angled triangles. So in right-angled triangles, we use SOHCAHTOA to find unknown sides and unknown angles. So let's look at this triangle here. So referring to this 40-degree angle, we need to label the sides. The longest side, which faces the right angle, is the hypotenuse. This side here, which faces, doesn't touch the 40-degree angle. That's the side opposite this angle. And this side is adjacent this angle. SOHCAHTOA tells you which ratio to use. In this triangle, I have the side adjacent the angle and also the hypotenuse. So that's what A and H means here. Cos adjacent hypotenuse. When I have the adjacent and hypotenuse, I use cos. So I set up my equation cos of 40. Now, because A is listed first, adjacent goes on top. So it's cos 40 equals x over 12. So to solve this equation, I undo dividing by 12 by timesing by 12. So I just take cos 40 and times it by 12. Now my calculator needs to be in degrees mode for this, and the answer I get is about 9.19 units. All right, let's look at this equation here. So this time I have the adjacent side and the opposite side. Opposite adjacent, I use tan. So I have tan of angle equals opposite over adjacent. Now this time, when I'm solving, the x, the thing that I want to find is on the bottom. In the last example, the thing I wanted to find was on top. That's why I multiplied. But when the thing you want to find is on the bottom, you must divide. So instead of going 12 times tan 67, I need to put in my calculator tan divided by tan 67. And the answer I get, this time I'll just do to one decimal place, is about 5.1. So in this last example here, we're finding an angle. We still use the normal SOHCAHTOA acronym to tell us which ratio to use. So I have the opposite side and the hypotenuse. Sine opposite hypotenuse. So here I have sine theta equals opposite over hypotenuse. Now, whenever you're finding an angle using trigonometry, instead of using sine, cos, or tan in your calculator, you use sine inverse, cos inverse, or tan inverse. So you press shift and then sine, or shift and then tan, shift and then cos. So to get theta by itself, I just take the sine inverse. So the sine inverse of 6 over 10, and if my calculator is in degrees, the answer I get will be in degrees, and to the nearest degree it's about 37 degrees. So sine, cos, or tan when you're finding a side, sine inverse, cos inverse, or tan inverse when you're finding an angle. Now this SOHCAHTOA acronym only works for right-angled triangles. Let's now look at non-right-angled triangles. So in non-right-angled triangles, we have the sine and cosine rules to help us find unknown angles and sides. So these first two formula here are both for the sine rule. This is for finding a side, which we're going to do in this triangle here, and this is for finding an angle. They're the same formula, it's just if you want to find a side, side's on top, you want to find an angle, angle's on top. And this is the formula for the cosine rule for finding a side. So let's start with this triangle here. So let's say we want to find x. Now we can't label this triangle as opposite, adjacent, and hypotenuse like we did in the previous example. That's just for right-angled triangles. Instead, we label the sides A, B, and C. So big letters indicate angles. So angle A is opposite or facing side A. So if this side here is my A, then this here is my angle A. Sides and angles opposite. So the sine rule is saying A over sine of A equals, so B is like my x in this case, over sine of B. So the angle opposite that side. So now to find this value here, I've got x divided by sine 80. Sine 80 is just a number. So the way I undo dividing by sine 80 is timesing by sine 80. So I'm going to put this on my calculator, making sure I'm in degrees mode because the angles were in degrees. And I get x is approximately 23.6. So this is the side length of x. So now let's look at using the sine rule to find an unknown angle. Unfortunately, there's sometimes an ambiguous case. Ambiguous means double meaning. Sometimes when you're finding an angle using the sine rule, there are two possible values for that angle. So that basically happens when you're finding an angle that's opposite a larger side. So this angle is opposite a larger side compared to this side. This side's longer than that side. So when I use the sine rule to find this angle, there will be two possible values. One will be an acute angle, one will be an obtuse angle. So I'm just going to use this formula to find the first value. So sine of theta, that's kind of like my angle A. So what goes on the bottom is the side opposite that. Theta and 24 are opposite each other. And that's equal to sine B over B. So again, 40 degrees opposite 16, they go together. So to solve this equation, I'm going to multiply each side by 24 and take the sine inverse. So the reason that I'm now going to take the sine inverse, I'm finding an angle. So remember, I said on the previous slide, whenever you're finding an angle, you use sine inverse, cos inverse, or tan inverse. That's true whether it's a right-angled triangle or not. So will just be the sine inverse of all of this. So I can put that straight on my calculator. So putting this on my calculator, I get one possible angle about 75 degrees. That's to the nearest degree. So that's one possibility. The other possibility is that theta equals 180 minus that first answer that I got, which is 105 degrees. So in this particular triangle, a triangle drawn with these measurements, the angle opposite the 24 side could be 75 degrees. It could also be 105 degrees. So to deal with the ambiguous case, just get your first answer as normal and then subtract your first answer from 180 and see if it works. So the only time your second answer would not work is if it would make the angles in the triangle add to more than 180. So this is an example where there's an ambiguous case because I was finding an angle opposite the longer given side. All right, let's move on to this one here. So this is using the cosine rule. So make sure you know when to use each one. So here, when I found a side using the sine rule, I had two angles and a side. For the cosine rule, I use this to find a side when I have two sides and the angle in between. So you use the sine rule and cosine rule under different circumstances. So the cosine rule is generally easier. We don't have any ambiguous cases to deal with or anything like that. So once again, side C is opposite angle C. So if this is my side C, the one I'm trying to find, this is my angle C. So A and B are both 16. So I simply have x squared equals a squared plus b squared minus 2 times a times b times cos of angle. So I'll put that straight into my calculator. So if I put all that into my calculator, I get the answer about 600.908. That is not the answer, that's x squared. So x will just be the square root of the answer I just got. So if I put that on my calculator, the answer I get is about 24.51. That is side length x. All right, now let's look at an example where I could apply the cosine rule. So bearings are one application of trigonometry. Let's do this question. Two hikers, Gary and Harry, set out from the same point. Gary goes for 6 kilometers on a bearing of 335 degrees. Harry goes for 12 kilometers on a bearing of 100. How far apart are the two hikers? And what's the bearing from one of them to the other? So let's start by drawing a diagram. So when we're drawing bearings, we'll start with a little compass. So bearings go, of course, north, east, south, and west. So it's the angle made with the north axis going in a clockwise direction. So north is 0 degrees, east is 90, south is 180, and west is 270. North is like 0, but also 360. So if Gary went for 6 kilometers on a bearing of 335, he went up here northwest. So this angle here would be 25 degrees because, of course, 335 plus 25 gives you 360. So he's gone in that direction. Harry's gone for 12 kilometers on a bearing of 100. So if east is 90 degrees, 100 degrees is just a little south of east. So he's gone here. His line will be much longer because he went for double the length. So this angle here would be 10 degrees because 90 plus 10 is 100. So what we want to do is make this into a triangle. So I can just join up the last side of the triangle. So I have one side here that's 6 kilometers, another side that's 12, and I have the angle between them. It'll be 10 plus 90 plus 1 plus 25, sorry. So that'll, of course, mean this whole angle is 125. So to find the distance between them, which I'll call x, I just use the cosine rule like I did on the previous slide. So using the formula c squared equals a squared plus b squared minus 2ab cos c, I put this in my calculator, and I get something like 262.595. That's x squared, not x, so x will be the square root of that, which is about 16.2 kilometers. So that is the distance between them. Now, to find the bearing, so I have Gary up here and Harry here. I want to find the bearing from here to here. So what I should do is draw a compass at my starting point again. So to find the bearing, I'm going to need to find this angle in here. So to find that angle in here, I could use the cosine rule for angles or the sine rule. So I'm just going to use the sine rule to find this angle here. Now this time there will not be an ambiguous case because the angle I'm finding is not opposite the longer side. This side is the longer side. So there's going to be no ambiguous case here. This angle here must be acute. So I have sine A over A equals sine B over B. So notice when I wrote B here, X, I used a few more decimal places than just 16.2 so I can be as accurate as possible. So theta will just be the sine inverse of, so I'm going to times the fraction by 12. You only times the top by 12. 12 sine 125 over 16.20478. So I put that straight on my calculator. So putting that in my calculator, the angle I get is about 37.344 degrees. But that is not the bearing. That's just this angle here. What I need to do to find the bearing, remember it's the angle made with the north axis going in a clockwise direction. I actually need this angle here. But I know that this angle here was 25. So that means this angle here is 25 because they are alternate. This angle here and this angle here, there's the Z shape because this red line and this green line are parallel because they're both pointing due north. So what this means is this whole angle that I'm looking for is going to be 180 minus 25 minus the value I just found for theta. So the bearing is 117.656, and that does make sense because we know to go from Gary to Harry, we're going in a southeast direction. So I should get an answer between 90, which is east, and south, which is 180. All right, let's now move on to radians. So radians are just another unit of measurement for degrees. It's like, if you were to measure the side of a rectangle, you could use centimeters or inches. They basically do the same thing. And so it is with radians and degrees. So let's define what 1 radian is. So let's say I have a circle here, radius of 1. And let's say I draw it such that this arc is the same length. It's also 1. If I draw a circle and this little sector in this way, it turns out this angle here is always fixed. It's always going to be about 57.3 degrees. That's rounded. We define this angle as 1 radian. So 1 radian is just 57.3 degrees. 1 radian is the angle made when you draw a sector with radius 1 and the arc length is also 1. So we know that there would be 2 pi radians in the whole circle because the circumference of this circle is 2 pi r. If r is 1, the circumference is just 2 pi. So there are 2 pi radians in a full circle, but a full circle is 360 degrees. So 2 pi, which is about 6.28 radians, is equal to 360 degrees. So pi radians, 3.14159 radians, is equal to 180 degrees. So you can easily convert between radians and degrees. So if I'm in radians and I want to go to degrees, all I do is times by 180 over pi. In a sense, you're timesing by 57.3 degrees. This number here is 180 over pi. If you want to go degrees to radians, you just do the opposite. You times by pi over 180. So, for example, 30 degrees, if I want to convert it to radians, I times it by pi over 180. So I get 30 pi over 180. That's in radians. So if your calculator doesn't give you exact values, what you can do is you can just simplify the 30 over 180 and then write pi. So 30 over 180 is 1/6. And then we can just write the pi on top. 30 degrees and pi over 6 radians are exactly the same angle. So if I have something like 3 pi on 2 radians, and let's say I want to convert that to degrees, you can actually just put 3 pi over 2 times 180 over pi on your calculator, and it will give you 270 degrees. So one thing that's really cool about radians, it gives us an easy way to calculate arc lengths. The arc length in a circle is just the radius times the angle theta, where theta is in radians. You can only use this formula if the angle's in radians. So if I wanted to calculate this arc length here, arc being part of a circumference, this part here, sorry about my inaccurate pen here. If I want to calculate that arc length, it's very simply radius, which is 3, times the angle in radians. Pi over 6 is 30 degrees, as we saw up here. So the arc length is just 3 times pi over 6, which is pi over 2, or about 1.57 units. Let's now look at calculating area of sectors using radians. So it turns out to find the area of a sector, you use this formula here. Area equals half theta times r squared. Now, theta, again, must be in radians. We also have a formula to find the area of a triangle. It doesn't matter whether we're in a circle or not. The area of any triangle is half AB sine C. So remember, A and B are side lengths because they're small letters, and C is a big letter, so it's an angle. You use this when you have two sides and the angle between them. You can find the area of the triangle even though you don't know its perpendicular height. So what we're going to do is we're going to combine these two here to do this question here. I'm going to find the area of the shaded part if the circumference of this circle is 10 pi. So I'm going to find this shaded area here. The way I'm going to do it is I'm going to find the area of the sector and subtract the area of the triangle. So let's go through that. The first thing is, I don't actually know what theta is, this angle here. I need this to be able to find the area of the sector. I also need an angle to be able to find the area of the triangle. So I'm going to start by finding what theta is. Now, this is the one thing I didn't go through before. I'm going to use the cosine rule for an angle. You use the cosine rule to find an angle in a triangle when you know all three sides. Now, I know this side is 4, and I can easily find these two sides here. Now, they will be the same because they're the radius of the circle. If the circumference of the circle is 10 pi, remember the circumference is equal to 2 pi times the radius. All I need to do is divide each side by 2 pi. So 10 pi over 2 pi is 5. The radius of this circle is 5. Now what I have is a triangle here, and I know all three sides, 5, 5, and 4. So this is the formula for the cosine rule. You're finding an angle. So C, big C, is an angle. Remember, little c is the side opposite it. So the side opposite the angle you want to find, that's the one you subtract on top, and it doesn't appear on the bottom. So in this particular triangle, theta, that's like my angle C, so it will be the cos inverse of a squared. So we figured a and b are both 5. The one you subtract is the side opposite the angle you're trying to find. So here, 4 is opposite the angle I'm trying to find. So 4 gets subtracted. It also does not appear on the bottom. So that is the formula I use to find theta, and I can put this straight in my calculator. Now, because I want to find the area of sector, and I need theta in radians, it would make sense that my calculator is set to radians, and then the answer I get here will be in radians. So I get 0.823 radians. So therefore, the area of the sector being this whole thing here, I can just use this formula very simply. And so putting this on my calculator, the area of the sector is about 10.29 units. So now I'm going to find the area of the triangle and then subtract. Now, when I'm finding the area of the triangle using half AB sine C, it doesn't matter whether this angle's in radians or degrees. It just matters your calculator's in the right mode. So I'm going to use C as 0.823 radians. So my calculator needs to be in radians when I do this calculation. So putting that in my calculator, I get an answer of about 9.165. So the area shaded red is just this minus this. So I'll just put AS for area shaded. It's just going to be about 1.125 centimeters squared. And then I'm done. Okay, now we're going to move on to exact values and the unit circle. So we're going to start with exact values from these two special triangles. So here we have a right-angled triangle. The two shorter sides are the same, so it is isosceles. Isosceles triangles have two equal angles. So this angle here must be 45 degrees, and this angle here must be 45 degrees. So it doesn't matter what I call these side lengths, so I'm just going to call them 1 each. It wouldn't matter if they were 2, if they were 3, whatever, we'd still get the same answer. Using Pythagoras, this would be the square root of 1 squared plus 1 squared, or root 2. So we can easily figure out some exact values for 45. So, sine 45 is opposite over adjacent, so it's 1 on root 2. But similarly, cos 45 is 1 on root 2. And tan 45 is opposite over adjacent. So that is equal to 1. It wouldn't matter if these sides weren't 1. If they were both 3, we'd get the same thing. We'd get tan 45 is 3 over 3, which is also 1. So let's look at this triangle here. This is a special triangle. It's a 90, 60, 30 triangle. When this angle is double this angle, it turns out the hypotenuse is double the shortest side. Now, in any triangle, the shortest side is always opposite the smallest angle. So, if I call this side here 1, again, doesn't matter what I make the side length, it would work regardless. The hypotenuse is double that. So, if this angle's 30, we have 1 and 2 here. Using Pythagoras, this would be the square root of 3. So we can find the values for sine cos and tan of 30, 60, and 90. So let's start by looking at the 30-degree angles. Sine 30, opposite over hypotenuse. Sine 30 is equal to a half. Cos 30, adjacent over hypotenuse, is root 3 on 2, it's about 0.866. And tan 30 is 1 on root 3. Looking at 60 degrees, we have the opposite. So cos of 60 is 1 over 2, sine of 60 is root 3 on 2, and tan of 60 is root 3 on 1. So unfortunately, you just have to remember these exact values for 30, 45, and 60. And if we know these, we can use the unit circle to find all of the rest of them. So this is called the unit circle. It's a circle with center here at the origin. Its radius is 1. That's why it's a unit circle. So I know this is annoying. Now when I talk about an angle theta, I'm going to talk about the angle made with the positive x-axis going in an anti-clockwise direction. So the angles here are set up differently than they were for bearings. So let's say I have this angle here, theta, and I can make this into a right-angled triangle. This distance along here is whatever the x coordinate is at this point, also this point where it hits the radius, and this distance here is whatever the y coordinate is at that point. This distance here is 1 because the radius is 1. So sine theta is opposite over hypotenuse. Sine theta is whatever the y coordinate is, cos theta the x coordinate, and tan theta is sine over cos or y over x. So we define sine theta, whatever the y coordinate is when we draw a triangle that hits the circle, cos theta the x coordinate, tan theta y over x. So what we do is we start here, the angle made with the positive x-axis, so 0 degrees is the positive x-axis, we're going anti-clockwise, so it goes 90, 180, and 270. So to come up with a value for sine, cos, and tan of 0, the x-coordinate here at this point is 1 when the angle is 0 degrees, the y-coordinate is 0. So sine theta is the y-coordinate, cos theta is the x-coordinate, and tan theta is sine over cos 0 over 1. So we could also do the same for 90 degrees here. If the angle with the positive x-axis is 90 degrees straight up, so here the y-coordinate is 1, so sine of 90 is 1, cos of 90 is 0, and tan, we have a problem because it would be 1 divided by 0, so it's actually undefined. And we could do similarly for 180, 270, and 360. 360 and 0 are just the same. So 360 is going to be this. 270, the y-coordinate is -1, and the x-coordinate is 0. So again, tan will be undefined. It'll be -1 over 0. And at 180, the x-coordinate is -1. So cos theta is the x-coordinate. The y-coordinate is 0. And tan will be 0 over -1. So how are we going to come out with some of these exact values? Well, we're going to use the unit circle. So let's say we want to look at 120. So what we want is we want this angle with the positive x-axis anti-clockwise to be 120 degrees. So I could draw a triangle here. This angle inside the triangle is 180 minus 120. It's 60 degrees. So if I rub out this angle here and make that 60 degrees, we will have congruent triangles. These two triangles here and here are congruent. Now I know this distance here because cos of 60 is a half. This distance here must be a half. And similarly, if this angle is 60, this distance here will be root 3 on 2, because sine 60 is root 3 on 2. Now, because these two triangles are congruent, this distance will be the same as that. It will also be root 3 on 2, and this distance will be 0.5. So this point here on the circle, the x-coordinate is now negative. It will be negative a half, or negative 0.5. The y-coordinate is still positive. That will be the point there. So this distance is a half. This distance is root 3 on 2. Now we said cos of theta will be the x coordinate. So cos of 120 is actually minus a half, but sine of 120 is still positive. It's root 3 on 2. Tan is sine over cos, so it's a positive over a negative. It is going to be negative here. So note, in this quadrant, the x and y coordinates were both positive. So sine and cos are both positive, and tan would also be positive for that reason. In this quadrant, only the y coordinate is positive, so only sine's positive. Here, x and y are negative, so sine and cos are negative, but tan and negative divided by a negative is positive, and similarly cos here. So remember, this is like all students take calculus. These letters tell you which is positive. All are positive in the first quadrant, only sine, only tan, only cos. So we can figure out these other exact values too, and I'll give you an example using 225. So 225 is between 180 and 270. It will be here. So I want this whole angle here to be 225. So I'm going to draw a triangle in here. This acute angle there will be 45 degrees because 180 plus 45 is 225. So if I turn this into a right-angled triangle like this, it will be congruent to a right-angled triangle here where this is 45 degrees. So I know that this distance and this distance will both be 1 on root 2. This distance is just the x coordinate. It's cos of 45. This is sine of 45. And that's the same down here. This distance will be 1 on root 2. This will be 1 on root 2. The only difference is at this point, both of them will be negative. So that point there is minus 1 on root 2, minus 1 on root 2. So tan 225 is going to be this divided by this. It's just going to be 1. It's going to be the same as tan 45. Cos of 225, well, it's the same as cos of 45, but now cos is negative in this quadrant. So cos is the x value of that point, and sine is the y value. And we can do similarly for 300 and 330. So we've now filled our tables with a lot of exact values. There's no way, however, you're going to remember all these. So what you should do is just try and remember these 30, 45, and 60, and remember how the unit circle works. So we're now going to use the unit circle to help us solve a trigonometric equation. So let's say I want to solve this trigonometric equation and find all solutions for x between 0 and 360. So let's have a go at this. So what we're going to do is we're going to undo the other stuff first before the cos. So my first step here, undoing things in the opposite order to BODMAS, I'm going to add 1 to both sides. So if I add 1 to both sides, I get 3 cos of 2x is equal to 1. Now I'm going to divide each side by 3, and I get cos of 2x is equal to 1/3. So now to go further, I need to take the cos inverse of both sides. So what I'm going to have is that 2x equals the cos inverse of 1/3. Now this may look really simple. You probably think, well, I'll just put this in my calculator. The problem is if you put cos inverse of 1/3 in your calculator will give you only one solution. There is actually another solution between 0 and 360. So let's investigate this. So if I put cos inverse of 1/3 in my calculator in degrees mode, I get one solution, cos inverse of minus 1/3, is about 70.53 degrees. So that's all well and good, but the unit circle shows us how to find the second solution. So remember the unit circle here, it has radius 1. So what it's telling me, what this thing here tells me, is that if I draw a triangle like this, and that angle there is 70.53 degrees, What that means is that at this point here, the x-coordinate will be a third. We don't really care what the y-coordinate will be because we're only interested in cos. But there will be another solution. There will be another time on the circle where the x-coordinate, remember the x-coordinate is cos, where the x-coordinate will be a third. And that will be down here. This point here will also have an x-coordinate of third, and we don't really care about its y value. So that will happen when I draw congruent triangles. This angle here will also be 70.53 degrees. But remember, we're interested in not the angle going this way, which is anti-clockwise. We want the angle going this way. So this whole angle here will be 360 minus 70.53 degrees. So it'll be about 289.47. So if I ask you to solve cos inverse of a third to find out what that is, it could be 70.53 or 289.47. There are two possible solutions. What we need to do is we need to take both of these equations and solve them. So what I mean by that is I could have 2x equals 70.53, which would mean x is just half of that, which is about 35.265, or I could have 2x is equal to 289.47, which means x is 144.735. So I found two possible values for x that if I insert them into that equation, they make it true. Now I want to find all solutions between 0 and 360. It turns out that there are more. So to investigate this, I need to rub this out. So please pause and copy it down if you need. So I found cos inverse of a third is 70.53. I also found that it could be 289.47. Now it turns out if you add 360 to any angle, it's the same angle. So for example, if I have this angle here as 10 degrees, that's the same as 360 plus 10, which is 370. So cos inverse of a third actually gives you heaps of solutions. So it gives you 70.53, it gives you 289.47. They're the two solutions between 0 and 360, but I can add 360 to any angle. So I could add 360 to this, and I would get 430.53. I can add 360 to this one, and it would give me another solution. So 360 plus that would be 649.47. All of these solutions works. If you take the cos of any of these angles, you will get a third. So I need to also solve 2x is equal to 430.53. Because even though this is more than 360, when I divide it by 2, I'm going to get 215.265. That is between 0 and 360. I also need to solve 2x is 649.47. So dividing that by 2 gives me 224.735. So these are all the possible solutions for x. And I know that there will be no more. So normally if you're solving a trigonometric equation, there are two solutions between 0 and 360. But if you have something in front of the x, that changes the number of the solution. It's 2 times whatever this number is the number of solutions. So if this was a 3x, I'd expect 6 solutions between 0 and 360. All right, let's now move on to trigonometric graphs. So for trigonometric graphs, we're going to use the unit circle. So we're going to start by graphing y equals cos x. So what we found out from the exact values on the previous slide, cos of 0 is 1, cos of 90 is 0, cos of 80 is minus 1, cos of 270 is 0, and cos of 360 is the same as cos of 0, it's 1. So the cosine graph looks like this. It's a curve that goes down and up, and if I were to keep going past 360, it'd keep going down, up. It'd keep going down, up, periodically. So if I were now to graph y equals sine x, so from those table of values, sine 0 is 0, sine 90 is 1, sine 180 is 0, sine 270 minus 1, and sine of 360 is 0. So it kind of looks the same here. It just starts at a different position. So this is the graph of y equals sine x. So these are essentially the same graph. What I mean by that is I could shift the green graph 90 degrees across and it would be superimposed. It would lie on top of the yellow graph. Or I could take the yellow graph and shift it 90 degrees left. So a simple shift is the only difference between these two graphs. Now, the x-axis here is in degrees, obviously. If I wanted to put in radians, it would be the same graph. It's just that I would put x is pi on 2, pi, 3 pi on 2, and 2 pi. The y-axis wouldn't change. So these are the graphs of y equals cos x and y equals sine x. So remember when we were doing exact values, we had problems with tan at 90 and 270. Tan is undefined at 90 and 270. So if I want to graph y equals tan x, it's going to have asymptotes at 90 and 270. So from the exact values, I found that tan of 45 was equal to 1. Tan of 225 is also equal to 1. So the tan graph looks like this. The tan graph has all these different pieces. In fact, there's asymptotes starting at 90 every 180. There's one at 270, there'd be one at 450, 630, there'd be one at minus 90 over here. This is what the graph of y equals tan x looks like. So you can see it's totally different than y equals cos x and sin x. Cos x and sin x have no asymptotes, they just keep going down, up, whereas tan shoots off to infinity, then there's an asymptote, starts at negative infinity, shoots off to infinity, there's another asymptote. So now we're going to look at graphing equations of the form y equals a cos of all this and y equals a sine of all this. So all we need to do is look at the effect of the coefficients, the four coefficients a, b, c, and d. So starting with d, so d gives you the midline of the graph. So in y equals cos and sine x up here, the midline was the x-axis or y equals 0. That's because there was no constant term at the end. So a gives you the amplitude. So that's the distance from the midline to the maximum or the minimum. So for cos and sine, just by themselves, they have a maximum value of 1 and a minimum of minus 1. So remember, that's because of the unit circle. So remember, the x-coordinate and the y-coordinate were never more than 1 or less than minus 1. But it's also because of the SOHCAHTOA. Remember, cos is adjacent over hypotenuse. The adjacent side can never be more than the hypotenuse. Similarly for sine, it's opposite over hypotenuse. The opposite side can never be more than the hypotenuse. So because cos of this and sine of this can never be more than 1 or less than minus 1, they always have a maximum and a minimum. So the maximum is going to be the midline plus the amplitude, and the minimum is the midline minus the amplitude. So changing the values of A and D will also change the values of the maximum and the minimum values. So B has something to do with the period. The period is how long it takes for a cycle to repeat. In other words, it's the distance between maximums, or it's the distance between minimums. So here we can see for both cos and sine, the period's 360. Distance between the maximums and the minimums is 360. It takes 360 degrees for a full cycle to repeat. Same with sine. One cycle is 360 degrees. So B is actually, if you change this value here, it's the number of cycles per 360 degrees. So if I were to say change B to 2, then there would be 2 cycles per 360 degrees. So the period, which I said is the distance between maximums, that's just equal to 360 divided whatever B is. So the last one I haven't gone through yet is C, which is the phase shift. That shifts things left and right. So let's look at an example where we're given an equation to graph, and we'll go through all of these coefficients and what they mean. So I'm going to get rid of the tan graph. Please pause and copy it down if you need it. So let's say I want to graph this function here. So first we calculate the values of a, b, c, and d. So a is 3, b, the number outside the brackets here is 2, c, the number inside the brackets is minus 90, and d, the constant by itself, is 1. So what we can tell straight away is that the midline of this is going to be y equals 1. That's because d is equal to 1, and we know the amplitude is 3 because it's the value of a. So what that means is I can draw the midline here. This will sort of cut the graph in half. So it's at 1 because d is equal to 1. Now the amplitude's 3. It's going to go up 3, so its maximum's at 4, and its minimum is going to be down at minus 2. So we know because b is 2, there are going to be 2 cycles per 360 degrees. So we know the period is going to be 360 over b, which is 180 degrees. The distance between maximums will be 180 degrees. So we know basically where we're going. We know it's going to be between 4 and minus 2. We know that it's going to hit its maximum, come down, it's going to hit its maximum 180 degrees later. The thing we don't really know is where the maximums actually occur. Do they occur at 0 and 180 or 90 and 270? So what we're going to do is do a bit of algebra to solve this. Now we know that the sine graph, it has a maximum at 90 degrees. So that means the maximum of this function, because it's a sine graph, it will occur when what's in the brackets is 90 degrees. Because if you take sine of 90, you get a maximum. So if I solve the equation 2 outside of x minus 90 equals 90, we can divide each side by 2 and then add 90. I get x equals 135 degrees. So this graph will be at a maximum at 135 degrees. So 135 degrees is here. It will go through this point there. So because the period is 180 degrees, its maximum will occur 180 degrees later at 315. So 315 is over here. It will be back at a maximum there. So because of that, it will be its minimum halfway between these two. If its maximum's at 135 degrees, its minimum will be down here at 225 degrees. Because the period is 180, it will also have a minimum at 225 minus 180 at 45 degrees down there. So if we want, we can calculate the y-intercept because that's really easy to calculate. All I do is let x equal 0. So I could just put in my calculator 3 sine of 2 outside of 0 minus 90 plus 1. So if I put that on my calculator, when x equals 0, I get y equals 1. So that means the y-intercept here is at 1. And we know everything we need to about this graph. So it's going to start at 1. It's going to go down, hit its minimum. It's going to come up, hit its maximum. It's going to go down, hit its minimum. It's going to come and hit its maximum. And then it's going to keep doing the same. It will go down and up forever and ever. So that is the graph, and we're done. So here we have the graph done. Now we're going to go and do the opposite, where you're given the graph and have to find the equation. So we're going to find the equation of this graph here. Now it could be a sine graph or a cosine graph. Clearly not a tan graph, no asymptotes. But we don't know whether it's a sine graph or a cosine graph. Remember, they're pretty much the same except for a phase shift. So I'm going to find an equation if this is a sine graph and also if it's a cosine graph. So regardless of whether it's a sine graph or a cosine graph yet, I know it's going to be of the form a equals cos of b outside of x plus c plus d, or it's going to be y equals a sine outside of b, x plus c plus d. Now, whether it's a cos or a sine graph, the values of a, b, and d will be exactly the same. So d is just the midline. It's halfway between the maximum and the minimum. So halfway between 5 and -3 is 1 along here. So D must be 1. The amplitude is the distance from the midline to the maximum. So from 1 to 5, it's 4. A here is equal to 4. So to find B, we can use the fact that 360 over B is equal to the period. So the period, remember, is the distance between maximums. So here we have, and I'm sorry if it's not 100% clear, but here we have a maximum at 30, and we have another maximum over here at 210. The distance between maximums here is 180. So B is 360 divided by the period, which is 2. There are 2 full cycles per 360 degrees. So now we have to find C. So the value of C will be different depending on whether we have a cos or a sine graph. It's actually really easy to find C for cos graphs, not as easy for sine graphs. So let's say, for example, that this is a cos graph. So I know from the values I've just calculated, if this is a cos graph, it will be y equals A cos B x plus C plus D. Now, I know that y equals cos x, those basic graphs that I graphed on the previous slide, y equals cos x normally has its maximum at x equals 0. Here, the maximum is 30, so we've shifted this 30 degrees to the right. So remember, for phase shift, it goes the opposite way that you'd expect. This number's negative if shifted right, and it is positive if shifted left. So if I've shifted the maximum across 30 degrees to the right, C would actually be negative 30. So this would be the equation if it was a cos graph. Now, finding C when it's a sine graph is a little harder. So we still know this would be y equals A sine B x plus C plus D. Now, normally, the maximum for the sine graph occurs at 90 degrees. So here it occurs at 60 degrees. So you might think, oh, cool, we've just shifted it across 60 degrees. Unfortunately, it doesn't work like that for sine graphs. Cos graphs were easier because we were comparing to x equals 0. Comparing to x equals 90 is a little more tricky. So we know that the maximum will occur when all of the stuff in the brackets here is equal to 90. So we want 2 outside of x plus c to equal 90. That's when the maximum of this, if it's a sine graph, will occur. But we know the maximum occurs at x equals 30. So I'm just going to replace x with 30. So I solve this equation. 2 outside of 30 plus c equals 90. So dividing each side by 2 gives us 45. I actually get c equals 15 degrees. Now, because the period is 180, I could add 180 to this and make it 195, or subtract 180 and make it 165, but I only need one value here. So I'm going to replace this c here with 15. And that is the answer for the sine graph. So the sine graph, I can't say it normally is at 90, now it's 30, therefore shifted 60. Sine is a little complicated. To find what C is, you need to solve what's in the brackets here equal to 90. All right, very last thing we're going to do, a bit of trigonometric modeling. So let's look at this question here. High tide at a beach 4 meters occurs every day at 6 a.m. The low tide is 1.2 meters and occurs each day at 6 p.m. So X is going to be the hours after 12 a.m., Y the tide length in meters, and we're going to look at the relationship between X and Y as trigonometric and find how many days it's less than 2 meters. So let's just draw a very rough sketch to show what's going on. So this is what's happening with the tide length, hours after 12 a.m. So at 6 a.m. every day, the tide is at its maximum of 4. And at 6 p.m., so 6 p.m. is 18 hours after 12 a.m. At 6 p.m., the low of 1.2 occurs. And this occurs every day. So it goes like this every day. It'll reach another maximum here at 30 at 6 a.m. the next day, and it'll reach another minimum at 6 p.m. the next day, and so on. This is periodic data. It goes, the tide length goes up and down, up and down, up and down, reaching a maximum of at 6 a.m. each day and a minimum at 6 p.m. each day. So periodic data like this is very well modeled by sine and cosine graphs, because they go up and down, up and down, up and down. So we're looking at how many hours per day the tide is less than 2. So what we want to do is we want to find out like 2 here, and we want to find how many hours a day it's less than this. So this here is 1 full day. 1 period is 24 hours. So let's come up with an equation. So the period here is 24 hours. So the midline of this graph, the halfway point, is going to be 4 plus 1.2 divided by 2, which is 2.6. So that means the amplitude is going to be 1.4. The midline at 2.6, the distance to the maximum or minimum is 1.4. So the period of 24 hours, that means B is going to be, if we're in degrees, 360 over 24, which gives us 15. So we could model this by a cos graph. The cos normally has a maximum at 0, but now it's at 6. Remember, maximums and phase shifts for cos graphs are a lot easier than for sine graphs. So we could easily come up with an equation here. It would be y equals a cos b, so we're in degrees here, x, so we shift 6 to the right, plus d. This equation models the tide. So to find out for how many hours a day it's less than 2, let's first find out when the tide length is equal to 2. It's exactly 2 meters each day. So what we're going to do is we're going to take our equation here and we're going to solve for y equals 2. So let's go ahead and solve this equation. So first thing we're going to do is minus 2.6 from both sides. Then we're going to divide each side by 1.4. So now we're going to take the cos inverse of both sides. So we get one solution from our calculator, which is about 115.377 degrees. So the other solution to that will be in the third quadrant. So this is equal to 180 minus about 65 degrees. So the other one will be 180 plus about 65 degrees. It will be 244.623 degrees. So now what we have to do is solve 15 x minus outside of x minus 6 is equal to both of these things. So if this is equal to 15 outside of x minus 6, all we do in both cases is divide by 15, divide each of these numbers by 15, and then add 6. And so what I get, x equals 13.692 or 22.308. So that means it hits 2 meters at these two times. So this is like 1 o'clock in the afternoon, and this is like 10 o'clock at night. So 1 o'clock in the afternoon is here when it hits 2, and then it comes back up to 2 meters at about 10 o'clock at night. So the difference between these two numbers is about 8.6. So it's about 8.5 hours each day that the tide length is below 2 meters. All right, we're finally there. Sorry for such a long video. Best of luck studying. You're a superstar. You'll ace it. This has been the luckiest maths teacher in the world. Have a great day.